Welcome back to the deep dive. Today we're cutting through the noise a bit.
Yeah. What are we tackling?
We're going to tackle a core challenge throttling modern AI. It's the insatiable hunger of large language models.
Ah, yes. The compute costs.
Exactly. We all know their incredible power, nuanced reasoning, generating creative content, all that cool stuff.
But that power comes with equally immense, often prohibitive computation and memory demands. It's a huge barrier.
It really is. And this reality, it's largely confined advanced AI development and, its broad application to just a select few.
The ones with hyperscale resources? Precisely. It's not just the sheer processing power, the FLOPs, during training either.
No. What else?
Well, the memory footprint, especially for storing model weights and the key value, or KV cache, during inference. That represents a fundamental bottleneck.
Right, so deploying these powerful models broadly is incredibly challenging.
Accessible mainly to organizations with vast specialized infrastructure. It limits who can even play in this space.
And that's precisely the problem today's subject, Mixture-of-Recursions, or more, aims to solve.
More. Oh.
This isn't just like an incremental improvement. It's being presented as a pretty groundbreaking solution.
Designed to do what exactly?
Designed to achieve the impressive quality of these large models without incurring their massive cost. Moore's core mission is, to fundamentally transform the cost-effectiveness of building and running advanced AI.
Okay, that's a bold claim. So our deep dive today is all about unpacking the technical ingenuity behind Moore then.
Exactly. We'll explore how it drastically improves efficiency while maintaining and sometimes even enhancing performance.
Sounds good. We'll need to dissect its core mechanisms, look at the experimental proof.
Right, see if it validates the claims, and then discuss what this all means for the future of AI.
It sounds like a fascinating look at how architectural innovation can, reshape the landscape of what's possible. Let's get into it.
So, okay, we've identified the Achilles heel of modern AI, this insatiable hunger for compute and memory. But how did we get here? And what have researchers tried so far to, tame this beast?
Well, standard transformer networks, they've revolutionized AI, right? They enable incredible abilities like few-shot generalization, complex reasoning.
Yeah, the stuff that really impresses people.
But those capabilities demand immense computational resources and memory. It makes training and deployment outside of hyperscale data centers incredibly challenging.
Which, like we said, limits who can even participate in advanced AI development.
Exactly. And the issue isn't solely the FLOPs needed during the initial training. That's a big part, sure.
But not the whole story.
No. It extends directly into deployment and inference. The memory required for model weights, which can be hundreds of billions of parameters.
Huge numbers.
And especially the key value cache, the KV cache, that builds up during autoregressive decoding. That's a fundamental bottleneck.
Explain that a bit more, the KV cache.
Sure. So each time the model generates a token, a word or part of a word, it adds new key and value pairs to this cache. For long sequences, this cache just grows and grows, and it rapidly saturates the GPU memory.
Ah, okay. So that's the practical constraint limiting how widely we can deploy these powerful LLMs.
Precisely. Given these hurdles, researchers have naturally pursued efficiency. Makes sense.
Right. So what are the main avenues?
Well, one pathway is parameter efficiency, basically reducing the total number of unique parameters in the model.
How do you do that?
Think of things like layer tying. Instead of having distinct weights for every single layer in the network.
You reuse the same weights.
Exactly. You reuse the same weights across multiple layers. This dramatically cuts down on the unique parameters the model needs to learn and store.
Got it. Like having one really versatile chef instead of a whole brigade for every dish.
It's a good analogy.
Yeah.
Techniques like those in universal transformers exemplify this. They allow for greater effective network depth without inflating the actual parameter count.
Okay, so that's one approach. Parameter efficiency. What else?
Another direction is adaptive computation. The core idea here is that models dynamically allocate resources.
Meaning
not every token requires the same amount of thought or processing. Some parts of the input might be simpler than others.
Right, like predicting the fat versus predicting a complex technical term.
Exactly. So approaches like early exiting allow models to dynamically stop processing earlier when predicting simpler tokens, spending more compute only where it's truly needed.
Okay, that makes sense too. Smarter resource use. So that we have parameter efficiency for leaner models and adaptive computation for smarter resource use.
Correct. But here's the missing link Moore addresses. An architecture that truly unifies both of these approaches has been, elusive.
Really? People haven't tried combining them.
Oh, they've tried. Recursive transformers, for instance, lead a foundation with built-in weight sharing, which helps parameter efficiency. But prior attempts at making that recursion dynamic, the adaptive part, often faced practical hurdles. Or they just defaulted to fixed depth computation anyway.
Meaning every token got the same processing regardless of complexity, kind of defeating the purpose of adaptivity.
Exactly. So despite progress on each axis, that effective unification was missing.
And this is where more comes in. Here's where it gets really interesting.
Right. Moore introduces its grand unification. It's not just crudely combining two techniques. It's
Yeah.
integrating them seamlessly within a single, cohesive recursive transformer framework.
And adding that dynamic token level control.
Precisely. That's the key to fully leveraging these recursive architectures.
So how exactly does Mayer manage this, bringing these two efficiency goals together? What are the core mechanisms?
Okay, first for parameter efficiency, like we touched on, it reuses a shared stack of layers across multiple recursion steps. This dramatically cuts the number of unique parameters.
Fewer weights to store and train? Makes sense.
Then for adaptive computation, it introduces these lightweight components called routers.
Routers. What do they do?
These routers dynamically assign different recursion depths to individual tokens, so a complex word might get routed through the shared layers more times.
While a common punctuation mark might only get 1 or 2 passes.
Exactly. Only as much thinking time as it needs. Very efficient.
Okay, that's clever. And does this dynamic routing have other effects?
It does, and this is crucial. It has a ripple effect on attention and memory. Because only some tokens are active at deeper recursion levels, Moore can focus the quadratically scaling attention computation only among those active tokens.
Ah, avoiding wasted compute cycles on tokens that are already done.
Precisely. And crucially, it also selectively caches only the key value pairs, the KV cache we mentioned, for those active tokens at each recursion depth.
So the KV cache itself becomes dynamic and smaller?
Yes, this recursion-wise KV caching drastically improves memory access efficiency and reduces I/O demands. That's critical for inference speed and cost.
Wow. And you mentioned a KV sharing variant too.
Right. There's also a variant designed specifically to decrease prefill latency and the memory footprint even further. It does this by reusing the KV pairs from the very first recursion across all subsequent steps.
Maximal memory savings then.
Maximal memory savings, though, as we'll see. It comes with some interesting trade-offs in performance.
Okay, so taking a step back, this isn't just an incremental improvement. It sounds like a potential game changer.
That's the claim. Moore is charting what they call a new Pareto frontier,
Meaning?
meaning you can potentially get better quality, lower perplexity, higher few-shot accuracy with less training compute and smaller model sizes, and higher throughput during inference.
Better results, lower costs, faster speeds. That's quite the promise.
It is. The broader implication here is that Moore could make powerful language models far more accessible and deployable.
So for you, the developer listening, building on these models, what does it mean?
It could mean substantially lower operational costs, faster response times for your users, and potentially the ability to deploy more capable models on hardware that's less expensive.
This isn't just an academic win then. It's potentially democratizing advanced AI.
That's the hope. Shifting it from being almost exclusive to hyperscale labs to a much broader range of innovators. It really could recalibrate our understanding of how efficiency drives AI innovation itself.
All right, let's peel back the layers now and really look at the technical innovations inside Moore. We should probably start with the foundation. Recursive transformers. How do they differ from standard ones?
Okay, so a standard transformer, builds token representations by stacking distinct layers. Each layer has its own set of weights.
One layer after another. Got it.
Recursive transformers, however, partition the model into, say, netter recursion blocks, but critically, each block uses a shared pool of parameters, let's call it.
A shared set of weights reused multiple times.
Exactly. The beauty is you can increase the effective network depth, how much processing a token undergoes, without actually inflating the model's parameter size. More processing, same memory footprint for the weights.
That parameter sharing is key then. How is it done? Are there different ways?
Yes. The paper explores several strategies for sharing these parameters. Think of them as different patterns for reusing the same set of building blocks, the same layers.
Like looping through them?
Sort of.
Yeah.
There's cycle, which is like cyclic reuse layer 0, 1, 2, then 0, 1, 2 again. And sequence, which is more like consecutive reuse 0, 0, 0, then 1, 1, 1, and so on.
Okay. Any others?
They also look at middle variants. These preserve unique, specialized layers for the very beginning and the very end of the processing.
Like an entry and exit point.
Exactly. But then they efficiently reuse a core set of shared layers in the middle, using either the cycle or sequence pattern.
And did one strategy work better?
Yes, the middle cycle strategy emerged as the most effective in their experiments. It gave superior results in terms of negative log likelihood and accuracy.
Interesting. So that balance of unique entry-exit layers with shared cyclical processing in the middle seems to be the sweet spot.
It appears so. It suggests that having some specialized initial processing and final projection layers is beneficial, while the core iterative refinement can be done effectively with shared weights.
So what does this all mean in practice? It's not just about smaller models, right? You mentioned smarter training and faster inference, too.
Right. For training, especially large-scale distributed training, using techniques like FSDP, fully sharded data parallel.
Explain FSDP quickly.
FSDP shards the model parameters across many GPUs. Normally, each GPU only holds a slice. To run a layer, it needs to gather the full weights for that layer.
Okay.
With recursive models, because the same parameters are reused across narrow recursive steps, you only need to gather those shared parameters once per forward-backward pass, instead of gathering unique parameters for every single layer.
Ah, so NR computations for just one parameter gathering step. That sounds way more efficient.
It's a significant practical gain for large-scale training. Less communication overhead between GPUs.
Okay, and what about inference? You mentioned continuous depth-wise batching.
Yes, this is really neat because tokens at different stages of their recursion, maybe some are on pass 1, some on pass 2, are all using the same shared parameter block.
They can be processed together.
Exactly. They can be grouped into a single batch for that shared block. This eliminates those bubbles, the idle periods where the GPU might be waiting for a specific layer's computation to finish before starting the next. You keep the GPU highly utilized.
Which leads to significant throughput gains. Got it. It's leveraging that shared compute block repeatedly.
It really is. And it's a profound observation, actually. It makes you wonder,
What's that?
what fundamental property of these neural networks allows the same set of weights to be applied iteratively like this, to deepen processing without, suffering catastrophic forgetting or representational collapse?
Yeah, why doesn't it just mess things up or converge to nonsense?
It implies a certain robustness in the learned transformations. They can handle deeper, more abstract processing iteratively without corrupting prior computations or losing the ability to differentiate between processing stages. Quite remarkable.
It really is. And that leads us perfectly to the next big innovation. How Moore actually decides when and how much to apply this deeper processing, the adaptive part.
Right, the brain of Moore, its dynamic routing strategies.
So the core idea is dynamically adjusting recursion steps for each token during both training and inference.
Correct. A router component decides how many times that shared parameter block gets applied to each token. It determines the token's required depth of thinking, essentially.
Okay, how does this router work? Are there different types?
There are two main strategies explored. First, there's expert choice routing. This is inspired by top gating, like in mixture-of-experts models.
How does that work here?
At each recursion step, a router acts like an expert. It looks at the incoming tokens and selects its preferred top-needy tokens to continue processing deeper.
So it filters the tokens at each step.
Exactly. It creates a hierarchical filtering mechanism. Only the selected tokens are re-evaluated in the next recursion step, progressively narrowing the set of active tokens.
What's the advantage of that?
The major pro is that it guarantees a static compute budget. You know exactly how many tokens, k times the number of experts routers, are being processed at each step, which simplifies resource management.
Okay, that sounds efficient. But you mentioned a challenge earlier, something about causality.
Ah, yes. The potential causality violation during training. Because the router needs to decide which tokens are the top k, it might inadvertently use information from future tokens in the sequence to make that decision.
Which is a big no-no for autoregressive models that predict one token at a time. How does Moore tackle this?
It uses a clever trick, an auxiliary loss function applied directly to the main router itself during training.
What does this loss do?
It specifically pushes the router to produce scores very close to 1.0 for the tokens it selects, and scores very close to 0.0 for the tokens it doesn't select.
Aiming for like a clean separation.
Exactly. They call it achieving perfect separation in the router outputs at inference time. This ensures the router is decisive and avoids ambiguity, which is key to its precision.
It's like a smart filter deciding who gets to go deeper into the rabbit hole based on complexity but without peeking ahead. Almost binary.
That's a good way to put it. It learns to make that decision based only on the current state.
Okay, so that's expert choice. What's the alternative strategy?
The second strategy is token choice routing. This works differently. Instead of making a decision at each step, it commits each token to a full sequence of recursion blocks right from the start
Ow.
via a single routing decision. A router makes a top one gating decision, basically assigning each token to a specific expert, where each expert corresponds to a certain total number of recursion applications.
Ah, so the decision is made up front. What's the advantage there?
The major pro is it's inherently free from that causality leakage problem, because the decision is made once, based only on the initial hidden state of the token.
Okay, avoids causality issues. But does it have downsides? You mentioned load imbalance earlier.
Exactly. With token choice, you can inherently run into load imbalance. Some recursion depths or experts might end up assigned way too many tokens, while others get very few.
Which isn't great for efficient compute allocation if some GPUs are overloaded and others are idle.
Right. They try to mitigate this using a balancing loss regularization technique during training. This encourages a more uniform distribution of tokens across the different recursion depths or experts.
Does it work perfectly?
It helps, but the paper notes that token choice can still face convergence challenges, especially in heterogeneous expert settings, where different depths might learn very different functions. Achieving consistent load distribution across dynamically specialized computation blocks remains tricky.
So it seems the choice of routing strategy isn't just about performance numbers.
Not at all. It's about fundamental architectural assumptions, information flow, causal dependencies during training. Expert choice needs careful causality mitigation. Token choice struggles with load balancing.
It really highlights the deep challenges in designing these adaptive systems that optimize compute effectively on a per-token basis.
Definitely. Okay, shall we move on to the memory side? The KV cache.
Yes, let's talk key-value KV caching strategies, optimizing memory access. Remind us why the KV cache is so important, but also problematic.
Sure. The KV cache is absolutely crucial for autoregressive decoding, like generating text. It stores per-token key and value tensors from the attention layers.
And this prevents recomputing attention for all previous tokens every time you generate a new one.
Exactly. It avoids that quadratic recomputation cost. Without it, generating even a moderately long sentence would be astronomically expensive.
But the problem is,
The problem is, as you generate more tokens, this cache grows linearly with the sequence lengths. It quickly saturates GPU memory, especially for long contexts, becoming a major bottleneck for throughput and context length.
right, so how does More, with its recursive structure, address this memory bottleneck?
Moore introduces two tailored KV cache strategies. The primary one is recursion-wise KD caching.
How does that work?
With this strategy, KV pairs are cached selectively. Only tokens that are actively routed to a given recursion step actually store their KV entries at that specific level.
Ah, so if a token exits early, it stops adding to the cache at deeper levels.
Precisely. And the attention computation at each recursion step is then restricted only to these locally cached tokens for that step.
What are the benefits?
Substantial benefits. It significantly reduces the overall KV cache size compared to caching everything. This improves memory efficiency, frees up valuable GPU RAM, and reduces the input-output I/O demands for access in the cache.
Okay, that sounds like the default approach. What's the alternative you mentioned?
The alternative is recursive KV sharing. This one leverages a specific property of the architecture,
Which is?
that all tokens, regardless of their final recursion depth, traverse at least the very first recursion block.
Right, everyone goes through step one.
So instead of caching KV pairs selectively at every step, this variant caches them exclusively at that initial first recursion step. And then it reuses those same initial KV pairs across all subsequent recursion steps for that token.
Wow, okay, so you only store one set of KV pairs per token ever.
Essentially, yes. The benefit is maximal memory savings. You drastically cut down the cache size. The paper also highlights significant speedups, especially during the pre-fill stage.
That's pre-fill.
That's when you process the initial prompt before starting generation. By reusing the first step's KVs, you can skip the KV projection and caching operations at the deeper shared recursion steps during prefill.
That sounds like a huge win for latency and memory. Are there trade-offs?
Yes, there are trade-offs. While memory savings are maximized, the reduction in attention FLOPs, computation, isn't as dramatic as with recursion-wise caching because you're still attending back to that first step cache.
Okay.
And high KV can still potentially be a bottleneck during decoding, as all deeper steps need to access that single shared cache.
How does it affect performance, quality-wise?
Empirically, they found recursive KV sharing slightly degrades performance for the generally better expert choice routing. Interestingly, though, it can sometimes benefit the weaker token choice routing.
Why is that?
Possibly because providing that consistent contextual information from the first step helps stabilize or inform the token choice routing decisions across depths.
That is fascinating. And it's quite remarkable that KV sharing works robustly even with shared parameters, right?
It really is. It implies a deeper consistency in how these layers process information. Even when the same weights are applied iteratively, the learned representations seem to maintain enough structural resemblance that reusing the initial KV context works surprisingly well. The paper even shows visualization suggesting this.
These caching strategies are clearly critical. They directly impact how large a context window you can use, how many tokens per second you can generate.
Absolutely. For anyone running a chatbot, a content generation service, any LLM application really, these optimizations directly translate to potentially faster, more affordable operations.
Allowing you to maybe serve more users or handle longer, more complex prompts with the same hardware resources. Huge practical implications.
Okay, all this technical ingenuity sounds fantastic on paper, right? But the real proof, as always, is in the pudding. Does more actually deliver?
Well, the paper presents some compelling empirical validation. It seems to really back up the claim of doing more with significantly less.
Let's get into the main results then. What happens under an equal training compute budget, say 16.5 quintillion FLOPs?
Right. Under that fixed large compute budget, Moore achieved a lower validation loss, meaning it got better at predicting the next word, a key performance metric.
Better than the standard model.
Better than the vanilla baseline, yes. And it also achieved a higher average few-shot accuracy. The paper cites 43.1% for a Moore model with 2 recursions, Moore 2, compared to 42.3% for the vanilla baseline. Okay, better performance, but here's the kicker, right? The parameter count.
Exactly. This superior performance comes despite the Moore model using nearly 50% fewer unique parameters than the vanilla baseline.
Wow. How is that possible? Better performance with half the parameters.
The key reason cited is Moore's higher computational efficiency during training. It allows Moore to process more training tokens within that same fixed FLOP's budget.
Ah, so it learns more from the data within the same compute envelope.
Precisely. While the vanilla model might process around 20 billion tokens in that budget, the Moore model could process maybe 27 to 31 billion tokens. It's using its parameters more effectively to consume data.
And this holds up even with more recursion steps.
Yes, even as the number of recursions in R increases to 3 or 4, Moore maintains competitive accuracy. It consistently outperforms simpler recursive baselines and stays within a very tight margin of the full capacity vanilla model, despite the significant parameter reduction.
Okay, that's impressive under equal compute. What about under equal data, if you train both on exactly 20 billion tokens?
In that scenario, Moore 2 again outperformed both the vanilla and the simpler recursive baselines. It achieved lower validation loss and higher accuracy.
While using less compute this time.
Exactly. It used 25% fewer training FLOPs to reach that better performance on the same amount of data.
And does that translate to real-world savings?
It does. Compared to the vanilla baseline trained on the same data, the Moore model reduced the actual training time by 19% and cut the peak memory usage during training by 25%.
Why the savings there?
They attribute it mainly to that hierarchical filtering in expert choice routing and the recursion-wise attention mechanism. These effectively shorten the sequence lengths being processed at deeper levels, leading to a better compute accuracy trade-off even during the pre-training phase itself.
And the impact of specific design choices, like routing or KV caching.
The results clearly show expert choice routing generally outperforming token choice. For instance, 42.6% accuracy for expert choice versus 40.0% for token choice in one comparison. This really underscores the importance of precise dynamic compute allocation.
And the KV cache sharing.
As we discussed, KV cache sharing did result in a slight performance dip compared to the independent recursion-wise caching. However, it's framed as a very favorable trade-off, given the substantial memory savings and inference speed gains it offers.
Making it a pragmatic choice for deployment where memory is tight.
Exactly. It becomes an engineering decision based on your specific constraints.
So, bottom line, it's not just theoretical. We're seeing tangible benefits, cheaper training, less memory, faster inference, often without sacrificing, and sometimes even improving quality. That's a huge step.
It really is. But to truly assess a new architecture like this, you need to look beyond one or two data points. You need to examine its scalability.
Right, the isoflop analysis. Does it hold up across different model sizes and compute budgets?
That's the core question. Does performance continue to improve predictably as both model size and compute scale grow, following established scaling laws?
How did they test this?
They evaluated more across 4 different model scales, ranging from about 135 million parameters up to 1.7 billion parameters. And they did this under 3 distinct FLOPs budgets: low, medium, and high.
And they compared more to vanilla and simple recursive models.
Yes. Importantly, for the recursive and more models in this analysis, the recursion count, NR, was fixed at 3. This means these models had roughly 1/3 the number of unique parameters compared to their vanilla counterparts at each scale.
Okay, so what was the key finding regarding scalability?
The key finding is Moore's impressive scalability profile. Firstly, it consistently outperforms the simple recursive baselines across all the tested sizes and compute budgets.
Good start. How does it compare to the vanilla transformer?
This is where it gets interesting. At the small scale, 135 M parameters, Moore might slightly underperform the vanilla model. They suggest this could be a recursive capacity bottleneck. Maybe the shared layers aren't complex enough at that small size.
But what happens as you scale up?
This gap closes rapidly at scale. For models larger than about 360 million parameters, Moore not only matches but often exceeds the performance of the vanilla transformer,
Really? Exceeds it? When?
especially under the lower and mid-range compute budgets. The plots in the paper show Moore pulling ahead in those regimes.
That's a critical indicator, isn't it? That closing gap at scale.
Absolutely.
Yeah.
It strongly suggests that Moore's architectural advantages, the efficient use of parameters and adaptive computation, become more pronounced and more beneficial as the overall model complexity increases.
Making it a truly scalable and efficient alternative for future large-scale deployments, not just a niche thing for small models.
Exactly. It implies that Moore isn't just an optimization, it's potentially a fundamental architectural shift that holds promise for the next generation of even larger, more capable models.
Does this change how we think about scaling laws?
It might. Traditional scaling laws often focus heavily on just increasing parameter count. Moore suggests that how you use those parameters, the architectural efficiency, plays a massive role too. It raises the question, can Moore redefine the optimal path to massive model capabilities by shifting the balance away from just raw parameters towards more efficient, adaptive use of them?
Fascinating question. Okay, so it scales well in training. What about inference? Does it speed things up?
Yes. Moore also delivers significantly on inference throughput, accelerating deployment.
How? Is it that batching technique again?
Precisely. Its parameter-shared architecture is perfectly suited to leverage that continuous depth-wise batching we talked about.
Remind me how that helps.
By batching tokens that are at different recursion depths but using the same shared weights, it keeps the GPU highly utilized. It immediately replaces sequences that finish early with new incoming tokens, eliminating those bubbles or idle periods in the computation.
So faster processing. Do they quantify the speedups?
They do. The results are quite impressive. All the Moore variants they tested consistently outperformed the vanilla baseline in terms of throughput.
Even if the vanilla baseline also uses optimized batching.
Yes, even when the vanilla model leverages continuous sequence-wise batching, which is a standard optimization, Moore's depth-wise batching provides an additional advantage.
And does increasing the recursion depth in Moore help throughput?
It does. Increasing NAR generally leads to more tokens exiting early, which further reduces the average computation per token and also shrinks the active key cache size. Both factors significantly boost throughput.
How much faster are we talking?
In one configuration, Moore with 4 recursion steps, Moore 4, achieved up to a 2.06x speedup compared to the vanilla baseline.
Double the throughput. That's substantial. Is there any cost to that?
As mentioned, there could be a slight degradation in model quality, like accuracy, with very high recursion depths. But the paper frames it as a highly favorable trade-off, given the massive throughput gain.
Yeah, doubling speed for a tiny dip in accuracy might be well worth it in many applications.
Absolutely. Imagine cutting your LLM inference cost by half or more, or doubling the number of user requests your system can handle with the same hardware. That's the kind of practical bottom-line impact.
It directly translates to cost savings and faster user experiences. Huge.
It is huge. But while these speedups are impressive in their controlled experiments, it does raise some practical questions.
Like what?
Like, what are the remaining engineering challenges in really realizing these gains in diverse real-world deployment scenarios? For example, How do those variable length KV caches, which are dynamic because tokens exit at different depths, actually interact with the underlying GPU hardware architectures?
Beyond the specific optimizations like flash attention 2 they mentioned.
Right. The paper notes they exclude time spent on caching and updating KV pairs, assuming these can be optimized through various engineering techniques. But are those techniques themselves a significant hurdle, or are they straightforward?
The practical complexities of scheduling and managing variable length sequences efficiently on real hardware can be pretty non-trivial sometimes.
Exactly. So realizing the full theoretical potential in every deployment scenario might still require some clever engineering work.
Okay, let's try to unpack this even further. We know more is adaptive, but how does the model actually decide how much thinking each token needs? What's the logic?
Yeah, what's going on inside that router? This brings us to the router analysis section in the paper, which tries to uncover the semantic logic of dynamic depth.
Semantic logic. So it's related to the meaning of the words.
It appears so. What's really fascinating is a qualitative example they provide. They show a snippet of text and visualize the recursion depth assigned to each token by the router.
And what does it show?
It shows that the assigned depth aligns remarkably well with our human intuition about semantic importance. Content-rich tokens, important nouns or verbs like people or drugs, in their example, are shown passing through more recursion steps, say 3 steps.
While less important words.
Meanwhile, common function words like and or punctuation marks might only traverse 2 steps. Or maybe even just 1 step if they have moderate semantic importance, but aren't critical nouns or verbs.
So it's not just arbitrary filtering. The model seems to be learning to prioritize computation based on meaning.
That's exactly what it suggests. It's allocating more processing power where it's most needed for extracting deeper meaning and understanding the context. It's a compelling glimpse into the model's internal thought process.
And technically, how does the router achieve this precision? You mentioned that auxiliary loss earlier.
Right. When you look at the outputs of the expert choice router trained with that auxiliary loss, you see what they call perfect separation.
Meaning the scores are very clearly high or low.
Exactly. The output scores for the tokens the router selects to continue are sharply concentrated, very close to 1.0. And the scores for the unselected tokens are clustered very close to 0.0.
It's like the model has developed an almost binary switch. This token needs more thought versus this token is done processing.
Precisely. This decisiveness is key to its efficiency, ensuring compute isn't wasted on tokens that have already been sufficiently processed for their role in the sequence.
Okay, that gives us some insight into the routing. Now, what about scaling? If we want to build the next massive LLM using more, how should we approach it?
This is addressed by their compute optimal scaling analysis. It reveals a really unique growth pattern for more models.
Unique how?
They looked at performance under Isoflapley's constraints. So, for a given compute budget, what's the best model configuration? Moore exhibits a distinct compute optimal scaling behavior compared to the vanilla or simple recursive baselines.
What does that look like?
Its optimal path, the line connecting the best performing configurations across different compute budgets, has a notably flatter slope on their scaling plots.
A flatter slope, what does that imply? Model size versus data?
It implies that Moore benefits more significantly from increases in parameter count, essentially, building larger models than it does from simply feeding in additional data or extending the training duration for longer steps.
So it's relatively less data hungry compared to vanilla models.
That seems to be the implication. For a given compute budget increase, Moore suggests you get more bang for your buck by increasing the model size within the Moore framework, using more shared parameters effectively, rather than just training a smaller model for longer.
That offers a potentially different strategy for efficiently developing future, even larger, Moore models.
Exactly. If we connect this to the bigger picture, the optimal scaling policy for Moore models appears to shift. Instead of the traditional approach of scaling up data and compute somewhat in tandem.
Moore favors allocating resources to increase model capacity, using larger models trained for maybe shorter durations.
That's what the flatter slope suggests. It's a significant potential shift in scaling strategy that could influence future pre-training efforts for massive LLMs.
It challenges the prevailing scaling laws by introducing architecture efficiency as a major factor, not just raw size and data.
Right. It makes you wonder, will we see a move towards designing foundation models with intrinsically more capable but perhaps more compact building blocks, which are then applied iteratively and adaptively, like in Moore?
Interesting thought. Okay, one last piece of the puzzle. Test time scaling. What's that about?
This is another really powerful concept enabled by Moore's dynamic nature. It's about dynamic reasoning at inference.
So adapting during inference, not just during training.
Yes, Moore allows you to potentially allocate more recursion steps to tokens during inference itself, even more than it was trained with, and this can directly improve the quality of the generated output.
You give the model more thinking time on the fly for a specific request.
That's the idea. Hypothesis is that deeper recursion at test time doesn't just provide more raw compute. It might allow each subsequent recursion step to specialize further in refining the token representation or the thought process associated with that token at its particular depth.
Leading to better, more nuanced performance.
Potentially, yes. It's like the model dynamically decides, okay, this specific concept or phrase in the prompt is really complex. I need to delve deeper, run it through the shared layers a few more times right now, even if I usually stop earlier.
That sounds almost like how humans think sometimes, rereading a difficult sentence or pondering an idea longer.
It does suggest a fascinating parallel. It makes you ask, what is the underlying mechanism by which these deeper recursion steps specialize and refine representations, especially given they share the same weights?
Is it maybe like an internal, nonverbal chain of thought?
That's one possibility the paper gestures towards in related work. Perhaps the model performs a kind of internal deliberation or refinement across these shared layers without explicitly outputting intermediate reasoning steps.
So imagine a model that isn't stuck with a fixed thinking depth. It could adaptively delve deeper when faced with complex queries or ambiguous prompts.
On the fly, to give you a more nuanced, more accurate, more contextually aware answer. That's the promise of test time scaling.
It hints at a future where LLMs aren't just static endpoints, but can dynamically adjust their internal reasoning process based on the task's difficulty.
Which could drastically improve the quality of responses for complex situations without needing to retrain or fine-tune the entire model for every possible scenario. Hashtag ghetto outro.
Okay, so let's try and wrap up our deep dive into mixture of recursions, or more. We've covered a lot of ground.
We've explored its core breakthroughs, that really ingenious unified approach, bringing together parameter sharing and adaptive computation.
Right, using shared layers to drastically cut down the unique parameters.
And then using those lightweight routers to dynamically assign token-specific recursion depths, making sure compute is spent efficiently, only where it's truly needed.
And the empirical results seem to back it up.
They do. Impressive performance, lower validation perplexity, improved few-shot accuracy, often beating vanilla baselines.
And crucially, achieving this at equal or even lower training FLOPs with significantly smaller model sizes in terms of unique parameters. Plus, delivering that higher inference throughput thanks to clever caching and batching. It really demonstrates Moore as a potentially scalable and efficient architecture, offering a path towards getting that large model quality without necessarily incurring all the traditional large model costs.
Exactly. The key takeaway here, I think, is pretty profound. Moore makes advanced AI potentially more efficient and therefore more accessible.
It pushes the boundaries of what we thought was possible in terms of the trade-off between model scale, cost, and deployability.
It really feels like more than just minor tweaks. It's a fundamental architectural shift that could genuinely democratize access to these powerful language models.
Looking ahead, where does this research point?
Well, the paper itself mentions some fascinating future avenues. They discuss the potential for Moore, because it's adaptive, to perhaps learn to adjust its depth based on chain-of-thought style reasoning complexities.
So it might automatically think harder when doing complex reasoning.
That's a possibility. They also mentioned its compatibility with other efficiency techniques, like sparse algorithms, think pruning, or quantization for potentially even further gains, stacking efficiency methods.
That leads to a provocative thought, maybe. If Moore can dynamically allocate thinking depth based on semantic importance,
Yeah.
what if we could explicitly guide that allocation for specific tasks? Could you design prompts or methods that essentially tell the model, okay, for this part of the problem, think really hard?
Like directing the test time scaling, pushing it even further for specialized reasoning. That's an interesting idea. What kind of architectural changes or maybe training methods would you even need to enable that kind of explicit guidance? How do you inject that control?
Yeah, lots to explore there. For you, the listener, we really encourage you to consider the implications of this kind of efficient scaling. Think about it for your own projects, whether personal applications or maybe even broader societal uses of AI.
And if you want to get really technical, the researchers behind Moore have made their code available. The paper provides links, inviting further technical exploration of this deep dive.
Absolutely. And as always, to stay updated on the latest AI and ML research papers, you can visit our webpage. The link is in the bio.
Definitely worth keeping an eye on this space.
That's all for this deep dive. Until next time, keep exploring, keep innovating.